Okay, everybody, day 9, Calc 1, Chapter 3, Section 7. We're almost wrapping up the second week. That will be our halfway through point after today's lesson. So today we're going to talk about optimization problems, and there are some awesome examples in this book that are very well laid out. So I'm going to go over them this way, and if you have further questions about that, then please send me a text or email and I can go over them with you at greater length. So this first one is a classic. You have a farmer having 2,400 feet of fencing. He wants to fence off a rectangular field that borders a river. He needs no fence along the river. What are the dimensions of the field that have the largest area? So here you have fence that's 2,400 feet. You have to decide how it would be best. You're going to put 100 for the width here, 100 for the width here, and make it 2,200 feet across. Maybe 700 here, 700 here, 1,000 here, 1,000 here, 1,000 here, 400 here. What is the best way to do this? So we can do this by figuring out what the maximum area would be when we have this amount of fencing. So we take a look at the generic look at it. If we call our width x and our length y, we know that area equals x times y, right? And we have area equals x times y. The next thing that we're going to do so we can solve a system of equations is to figure out with the length, what would the length of the fence add up to be? Well, we have two widths and we have only one length, only one length because I don't have fence on this side of the river, okay? So 2x plus y equals 2,400. Now, from this equation, I can solve for y, moving 2x over here, and then I'm going to substitute this in for y for my area. So now my area formula is 2,400x minus 2x squared, okay? 2,400 minus 2x, 2,400x minus 2x squared. And I am on 251, by the way. Okay, so now we have a good formula for the area of what I'm talking about. So what I want to do is take the derivative of that because I want to find my maximum area. So in order to find a maximum or minimum of anything, I need to take a derivative. So the derivative of this is fairly easy, 2,400 minus 4x. So when I solve for my critical point, I'm either going to have, I'm going to set it equal to 0, and then I'm going to take this to the other side and divide by -4, and I will get 600. Now, maximum points will either, absolute maximums, will either happen at the endpoints or at the critical points. So technically you have to test them all to see which one would give you the best answer. And so if you test 0 and you put 0 in for x, the area is going to be 0. So that certainly doesn't work. And if you put 1,200 in, you're also going to get 0. So that doesn't work. So the answer will in fact be the 600 for the x value, and then that will yield 720,000 square feet. The closed interval method then will give this. So let's see, what else can we say here? If you want to go back and take a look at exactly how much it would be, we see that it would be 600 feet deep and 1,200 feet wide. Let's take a look. Okay, so it's going to be 600 deep, 1,200 wide. You add it up quickly in your head. Make sure you have 2,400. All right, so fairly easy optimization problems. Now the next one talks about a cylindrical can. Say you have a factory and you're wanting to produce a maximum amount of volume in a can with a minimized cost of metal. You can do that using calculus. So we're going to look at the cylinder here first. So let's first examine what a cylinder looks like as far as surface area, because we're talking about the material to make it. So we're looking at the surface area. Here I have my radius, here I have my height. A cylinder has a circle on the bottom, circle on the top, and this distance right around here will be the circumference times the height. This is a rectangle when I open it up. So knowing that, we can see that the rectangular sheet has the dimensions 2 pi r and h for area. So you'd multiply those together, 2 pi r h, to get that area. And if we substitute in for h, 1,000 divided by pi over r squared from this formula, then we can simplify and have our area formula with one variable. Now, you might say, well, do you have to bring it down so you're simplifying to one variable? There are instances where you might want to solve this, and actually in this example on page 253, it does show you an alternative method for using implicit differentiation to solve. So yes, sometimes you can use both variables and use implicit differentiation to solve, but I think it's easier if you just use a little algebra and substitute in, and then you can find your max and minimum that way. Alright, so the function we want to minimize will be our reduced function here, 2 pi r squared, and that's pi r squared top and bottom, plus our rectangle, 2,000 divided by r, and of course the radius has to be greater than 0, so we can also put that value in there for the domain. So to find the critical numbers, we're going to differentiate, and we get 4 pi r minus 2,000 over r squared. So remember, this r comes up and becomes r to the negative 1, and so when you use the power rule, you'll get negative, and then you subtract 1 from the negative 1, you get negative 2, so it will come down below. So we clean that up a little bit, and now we have 4 times the quantity, pi r cubed minus 500 over r squared. So when we set it equal to 0, we see that pi r squared is equal to 500. So if I divide both sides by pi and then cube root, I will see that the only critical number that I have is a radius that is a cube root of 500 over pi. Okay? So again, cube root of 500 over pi. Now, the domain of the area is greater than 0, because the area can't be 0, to infinity. So we can't really use the argument in example. The last example that we did is checking the endpoints. So we do have our critical value here that we're going to use. So r will be the cube root of 500 over pi, is an absolute minimum. Now, if we want to put that back in to solve for my h value, I will plug it in, simplify, and then I will get that's equal to 2r. So to minimize the cost of the can, the radius would be the cube root of 500 over pi centimeters, and the height would be equal to twice the radius, namely the diameter. Okay? All right. Example 3. Given a simple parabola This parabola is on its side. So we have, well, I have somebody who's printing on my printer, so that's coming through. So I'll pause a minute while that comes through. All right. So y cubed equals 2x, and the closest to the point of 1, 4. So we have a point 1, 4 that we're examining. Find the point that is closest to 1, 4. So we have a point up here. We have a parabola. We want to know what point on this parabola is the closest to 0.14. That's the problem. We're looking for the shortest distance between here and that point, and any point on the parabola. And they have this point as being an example of what could possibly be. So here you have to pull out some information from algebra. You have to look at the distance formula. The distance formula, you're going to subtract your x values and square it, plus you're subtracting the difference in their y values and squaring it and taking the square root of that. A lot of times we square and square root things because we're talking about distance, so that takes care of our issues with negatives. Now, we see up here again that the equation is y squared equals 2x. So if I divide by 2, I get x equals y squared, 1/2 y squared. So I can substitute that in. That way I can get down to just one variable. All right, now differentiating it, we'll get y cubed minus 8. Oh, put this down a little further, sorry. Y cubed minus 8. So we can observe that f prime of y is smaller than 0 when y is less than 2. And f prime of y is greater than 0 when y is greater than 2. So by the first derivative test for the absolute extremes, the absolute minimum occurs at 2. So when you set this equal to 0 and you solve, you will in fact get the value of 2. All right? So that will tell us that the corresponding point of x, then if I plug my value of 2 in for y, is also 2. So on the point y squared equals 2x, the parabola here, the closest point to 1, 4 is going to be 2, 2. Okay? Alright, now, next one, this is another classic problem. I think I did this problem when I was in high school. So, here we have a river. We have a man that launches his boat from point A on a bank of a straight river that's 3 kilometers wide, and he wants to reach point B, and which is 8 kilometers downstream. So they give you these two distances. I have 3 kilometer wide river. He wants to travel 8 kilometers downstream. Now he wants to get there as quickly as he can. So he's on one of these TV reality shows and he's trying to race. So he wants to find out what is the fastest way. Should he take the boat part of the way and run the rest of the way? Should he run all of the way? Or should he take the boat all of the way? And keep in mind that he's trying to figure out the quickest way to do that. Now, he can row 6 kilometers per hour. He can run 8 kilometers per hour. So where should he land to reach B as soon as possible? Now you might say, well, he should just run the whole way. Well, let's take a look and see if that's right. Okay, we're going to assume that the speed of the water is negligible compared to the speed at which the man rows. So we're going to say that he can row that speed in that type of water. Alright, so we have to find the distance between C and D. So we have this distance right here, and we may call that distance 8 minus x, or D to B. If we call this x, then this is going to be 8 minus x. So right here they said c to d is x as our unknown. If this whole thing is 8, then this is going to be 8 minus x from b to d. Alright, using Pythagorean theorem gives your rowing distance, the square root of x squared plus 9. Now we can use again, optimization problems often require us to pull out other information from science, and we have distance equals the rate times the time. We're going to solve that as time equals distance over rate. Again, distance equals rate times time. We want to solve for time, so we divide both sides by r and get time equals distance divided by rate. So now we have our rowing time as the square root of x squared plus 9 over 6, and the running time as 8 minus x over 8. So the total time, and this is the distance, this is the rate, the total time as the function would be those two added together. So that'll give me total time. So again, the rowing time would be the square root of x squared plus 9 over 6, because that's the rate of him rowing. The running time, 8 minus x over 8, because that's the rate of him running. And we're going to add those two together to see what the total time would be. Now, the domain of this function is going to be from 0 to 8. So if x equals 0, then he rows to C, straight across, he rows to C, and he runs the whole way. Let's take a look at the derivative. T prime of x over 6 times the square root of x squared plus 9 minus 1/8. And you, of course, are going to have to clean that up a little bit. So we're going to move our 1/8 over to the other side after setting it equal to 0. And when you clean that up, you will get 7x squared equals 81. So x will equal 9 over the square root of 7. Now, that is the only critical number. So we still have to compare it to the minimum, the endpoints, because we do have endpoints in this problem. So we have to look at 0, we have to look at 8, and we have to look at this critical point to see which one is the absolute minimum. So when I compare 0, I will get 1.5. When I compare 9 over square root of 7, I get 1.33 approximately, and t of 8 is 1.42 approximately as well. So the smallest of these values is right here at 1.33, so that would be my absolute minimum value occurring. So this man should land the boat about 9 divided by the square root of 7 kilometers, which is about 3.4 kilometers. He should come down and land the boat pretty much about where it's at on here, about 3.4 kilometers downstream, and then start running. Okay? Oh, sorry, I had that down. Okay, so let me go over that real quick again in case you couldn't see it. The 0 value is 1.5, and the 9 over square root of 7 is 1.33, and the 8 value is 1.42. This is my minimum value, so this is what is telling me that he's going to row the boat to 9 over square root of 7 kilometers, which is about 3.4 kilometers downstream from his starting point. All right. Finding the area of the largest rectangle that can be inscribed in a semicircle of the radius of r. So here we have a semicircle. We're going to look at the upper half of the semicircle, and then the word inscribes means that it's going to be inside, has 2 vertices on the semicircle, and 2 vertices are going to be on the x-axis. So we have here, 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 and here. Now, if this distance is x, then this distance would be 2x. And we're going to call this distance y. So our area of our semicircle is going to be 2y times, or I'm sorry, not the semicircle, the rectangle. The area of the rectangle is 2x times y. Now, we can eliminate the fact that xy lies on the circle so that y equals the square root of r squared minus x. We are only using the positive because we are looking at above the x-axis. So that's why that is there. So now I can take this y value and I can substitute it in here. And now I have a good function for my rectangle. Now, the domain of this is going to be greater than or equal to 0. You can't have a radius at 0. And it's going to be less than or equal to whatever my r value is, okay? So now we're going to take a look at its derivative. Okay, when we take the derivative of this, we will get 2 times the quantity r squared minus 2x squared over the square root of r squared minus x squared. Now, that is 0 whenever, looking at the top, if I take this and solve it for 0, I have r squared minus 2x squared equals 0. R squared equals 2x squared. That is where we're, right here we see that when we square the radius, we're going to have 2 times x squared. So if I solve that by taking, I solve for x, I'm going to divide by 2, take the square root of both sides, and I will get r divided by the square root of 2. Now, again, we know that x is greater than or equal to 0. So when we take the square root, we don't even pay attention to the negative. We know when we take the square root of something, it's plus or minus. But since we're talking about this area, we know we're not going to have a negative value. All right, so this gives us a maximum value of a. Since a is 0, we know that we're not going to use one of the endpoints. And this is our critical point. So if we plug this into our area formula, we will get r squared. Okay, now they give you a simpler solution here. If you're looking at the area of a rectangle using your trig functions, you can take a look at that on your own. Okay, so we talked a little bit about areas, material, surface area, volume, and even our running, boating running problem was a geometry problem involving figures. Where else would this be used? Business and economics is a big one. Business and economics for marginal cost, demand function. So if you're a business major, you have cost function. The marginal cost is the rate of change of C with respect to X. In other words, the marginal cost function is a derivative, C prime of X, of the cost function. Now let's consider marketing. If you're looking at the demand function or the price function, we would expect it to be decreasing function of X. If X units are sold, the price per unit, then you have the total revenue equaling X times your P of X, your price function. So, our profit function would be profit equals the revenue minus the cost. Profit equals revenue minus the cost. So real quick, let's take a look at the store selling 200 Blu-ray disc players, $350 each. Market survey indicates that for a $10 rebate offered to the buyers, the numbers will increase by $20 a week. Find the demand function and the revenue function. How large a rebate should the store offer to maximize its revenue? Okay, now we have the price function. Again, we're going to say the weekly sales increase is going to be X minus 200. For each increase of 20 units sold, the price decreases by 10. So for each additional unit sold, the decrease in price would be 1/20th times 10, and this is how you would get your demand function. Your revenue function would be X times your demand function. So now you have your revenue function. Your profit function, they don't want to do that yet. Okay, sorry, I went a little too fast. So let's take a look at revenue. When you take the first derivative of revenue, you get 450 minus X. Solve it equal to 0, and you can see X will be 450. So this value of X gives an absolute maximum by the first derivative to the corresponding price. And you'll see, excuse me, the corresponding price, once you plug it into the formula, will be $225. So the rebate, if it starts at $350, the rebate is going to end up being $125 to maximize the revenue. So the idea that they were going to offer a $10 rebate, that's okay. But if they offer a $125 rebate, they will sell more and they will maximize their revenue, which is their revenue minus the cost will end up more revenue, more profit. Okay? All right. Look, we're at the end of section 3.7. All right, if you have any questions on this, this is Wednesday evening for me. Tomorrow at 6, we will have a review session then, and test on Friday. Okay? All right. I'll talk to you guys soon.